Hello, everyone. Welcome to another CCEM web seminar. My name is Carmen Andrei, and I'm one of the TM operator in CCEM. Today, I'm going to talk about the liquid cell microscopy. I actually changed the original title from the liquid cell microscopy to introduction to liquid cell microscopy because I realized that almost each slide can be an entire seminar, and I cannot cover everything in 1 hour. So first, the outline of my talk. We're going to talk about why we should use liquid cell microscopy. Then I will talk about the application or the processes where liquid cell microscopy can be used. I will go through the types and system of the liquid cell. I will talk about the beam damage and beam sample interaction. I will cover a very important subject, the dose. I will talk about the resolution in the liquid cell microscopy. And at the end, I will present two of the analytical techniques which can be applied in liquid cells. And I will conclude with a few applications or practical cases from actually our group and a few from the literature. So the ones from the literature, I kind of group them based on the technique because we are a microscopy group. So why shall we use liquid cell microscopy? So traditionally, TM requires the sample to be vacuum stable inside of the microscope. Most of the samples prepared for TM are dried or embedded in a resin or epoxy, or sometimes they are flash frozen. All these methods have the potential to introduce artifacts in the preparation processes. These methods immobilize the sample, making it impossible to observe real-time dynamics. In-situ experiments like liquid cell microscopy give another dimension by observing live the events. Getting to understand dynamic events at nanoscale gives control to understand the structure of the materials. So in which application can we use liquid cell microscopy? So in energy storage, there is a need to understand and characterize the energetic reaction of materials. We can direct imaging key processing energetic reaction of materials. We can direct process the reaction during the battery operations, chemical changes in electrode materials. So in the catalysis field, we can change environmental conditions of chemical reactions and directly observe chemical, structural, and morphological changes. In the electronic devices, we can understand the working conditions or the test performance of new devices. In the material synthesis, we can simultaneously study the structure, processing properties, and performance in real time, like the oxidation reactions. In the biological dynamics field, we can understand the mechanism that controls biological processes like mineral formation. And in nanomaterials, we can directly observe the nucleation and growth reaction of nanoparticles. There are two types of liquid cell units, the closed unit cell and the open unit cell. The closed cells are typically built from 2 silicon wafers, each of coated with about 50-100 nanometer thick silicon nitride layer. A region of silicon about 100 microns across is etched out of each wafer, forming windows of silicon nitride. A spacer material such as silicon dioxide patterned onto one wafer keeps the windows at the correct separation. Closed cells are suitable for electrochemistry and heating capabilities. The open cells are used for liquids with low vapor pressures to help the decrease in resolution caused by the windows in the closed unit cells. In this case, droplets of liquids, like ionic liquids, are placed directly onto a supporting sample that includes a large area electrode. This sample is loaded into the microscope on a custom sample holder. The liquid is stable under vacuum, and electrons can pass through the liquid in regions where it is thin. These types of cells are used only for reaction mechanism in battery materials. The most common approach to form a liquid cell is to squeeze two chips together with an O-ring. This is the approach that has been chosen by commercial manufacturers of liquid cell systems. Clamping of the chip is combined with a design that preserves the seal between the microscope vacuum and the liquid. Clamp designs generally allowed both static and flowing liquid to be imaged. Fabricating the two chips separately offers advantages in choosing different design settings for different experiments. So there are different holders and companies on the market, like the Poseidon holder from Protochips, like the Stream from Dense Solutions, or the Hummingbird holder from the Hummingbird Scientific. They are all using different designs, but they are all based on clamp chips. More recently, our colleagues from Waterloo University come up with a new design which controls accurately the thickness of the liquid. The prototype holder, as far as I know, should be available in the next few months, and we are actually hoping to be among the first users. Our center has two Poseidon holders from Protochips, so in all my presentation, I will focus on their design. If you don't have a six-figure sum of money for a new holder, there are other options to do liquid cell experiments. Encapsulated methods like graphene cells are using a microscopic droplet of liquid between two atomic layer thick graphene sheets. There has been lots of development in this field with the second generation graphene liquid cell, which can be described as a liquid containing wells sealed by graphene covers. The third generation introduces a liquid channel in the graphene cells and requires a special design holder. Even though the best resolution achieved so far in the liquid cell was in graphene cells, currently graphene microfabrication procedures are still non-standard and require a lot of experience for successful results. Another option, and probably the cheapest one, I would say, is to use the K-kit from Pella company. The liquid is drawn inside the silicon nitrile windows by a capillary force, and the unit is sealed on both ends by a special glue. The cell can be used in any of the pre-existing TEM holders and only for static experiments. So in my presentation, I will focus only on the closed cell type liquid cell. Schematic of this cell is presented on this slide. So the liquid specimen is enclosed by two silicon nitride membrane windows supported by the silicon microchips. The thickness of the liquid is kept sufficiently small with respect to the mean free path length of electron sputtering in the materials. So the electron beam is transmitted through the sample for detection. It is also possible to flow liquids between the two silicon nitrile membranes using external tubing and syringe pump. So the Poseidon holder we have in the CCEM contains 3 integrated liquid ports with 2 inlets and 1 outlet. This design enables user to choose between static and flow experiments using only one holder. Electrical contacts are embedded into the holder, enabling the user to have options like heating or electrochemistry capabilities. Sealing gasket provides the seal to isolate the liquid to the vacuum of the microscope. A lid is attached with 3 screws to keep the assembly in place. A special lid is required for direct sight with the EDX detector, and I will talk about this a bit later in the EDX session. Each experiment requires a set of e-chips. The sample is assembled between a large and a small chip. There is a large variety of designs, and the user can mix and match e-chips to control the liquid thickness, flow parameters, heating, or electrochemistry. The liquid heating setup, in the liquid heating setup, actually, the large chip is the one which controls the functionality, allowing heating and electrochemistry in the same holder. Heating chips contains a metal heater that contacts the electrodes which are included in the holder. The sample can be heated up to 100 C. The electrochemistry system is designed to resolve the small currents while maintaining imaging and analytical data collection. The electrochemistry reactions are controlled with the use of a potentiostat, which measures and controls the voltage difference between working electrode and the reference electrode. The electrochemistry chips come in a large variety of electrode geometry and materials. The e-chip design minimizes the electrode area which is exposed to the liquid. All chips have 3 electrodes, the working electrode, the reference electrode, and the counter electrode. The working electrode typically is carbon or platinum, is always located over membrane window in the large chip, so it's always on the field of view of the microscope. What is really important in the case of electrochemistry experiments is to check the chemical compatibility of the holder. Some of the chemicals used for electrochemical reactions are not safe, either for the holder or for the TEM microscope. So a few years ago, we had an incident in one of our microscopes when the window broke and the acid actually spilled into the column of the microscope. So I can tell you it's not something really pleasant to fix or to repair. So before you start an experiment, check the chemical compatibility list, or you can contact the manufacturer. The electron beam can induce many artifacts during the imaging processes within a liquid cell. Both elastic and inelastic electron scattering can lead to beam damage. There are 5 types of beam damage that commonly occur in electron microscopy, summarized here by Ray Edgerton in this paper. The first one, the atom displacement and sputtering, is a type of beam damage due to high energy, high angle elastic electron scattering. This damage is not as significant as other types, except potentially when imaging crystalline formation within liquids. It can be mitigated by reducing the dose or lowering the energy beam. The electrostatic charging can be due to both elastic and inelastic scattering, although inelastic scattering has a dominant effect. In liquid cells, charge can build up on the silicon nitrile membrane. Such surface charge not only interferes with the incoming beam, but it can also induce unwanted particle movement within a liquid due to repulsion. A possible solution for that would be to use very high energy that has a bigger mean free path for scattering. So most of the beam will transmit to the specimen without generating secondary electrons. Reducing the electron dose rate can also reduce the total charging effect. Heating is another type of beam damage due to inelastic scattering of electrons, where part of their kinetic energy was converted to thermal energy. This can contribute to degradation of biological cells that are generally very sensitive to localized heating. Liquid flow system allows good heat exchange to prevent localized heating. Another type of beam damage is radiolysis, and it's the most critical beam damage mechanism in almost all liquid cell experiments. And I will talk about this on my next slide. Hydrocarbon contamination due to inelastic scattering is not very well understood within a liquid cell because it's really hard to distinguish its effects from those due to the radiolysis. Better cell preparation, including plasma cleaning of the chips before we put them in the microscope, or heating or electron beam shower can help get rid of the hydrocarbon contamination on the silicon nitride outside surface. Overall, using a high energy beam and a lower dose will mitigate most of the artifacts observed during TEM imaging of the liquid sample. The electron beam interaction with solid matter have been studied in detail in the past, but the situation in liquid is quite different. This is because of the high mobility of the species in the sample. High energy electrons generate primary and secondary radiolysis products. These products rapidly, actually in a few seconds, reach equilibrium concentration in the region irradiated by the electron beam. In the radiolysis of pure water, one product is hydrogen gas, which can produce bubbles if its steady state concentration is above the solubility limit. Another product is the hydrogen ion. The electron beam can change the pH of a solution under study, which can change the stability of the species in the solution. A third highly reactive product is the hydrated, or we call it the solvated electron. This species is thought to be responsible for the production of metallic cations in aqueous solution, leading to the phenomena observed in experiments that measure beam-induced growth of metallic nanoparticles and beam effects during electrochemical deposition. So one of the most important parameters using the liquid cell microscopy, and everybody talks about that, is the dose. The dose, the term that usually it's used in physics or in medicine, is the measure of the average amount of energy absorbed by a mass exposed to radiation. In the International System of Units, the dose is measured in gray, or in gray per second if we talk about the dose rate. There are literature studies and the reports dose similar with the electron flux, which is measured in electron per nanometer square per second. In liquid cell microscopy, dose is due to an electron beam incident upon of a thin layer of liquid, usually water. And there are two ways to calculate the dose rate. So we can use the grays per second using this function, or the most common way to use the electron per square angstrom per second or electron per square nanometer per second, using the beam current, exposure time, elementary charge, and the scanning area. So how do we actually measure the dose? So the most accurate way is by measuring the current using a Faraday cup holder under different conditions like aperture, spot sizes, with nothing blocking the beam. The second way is to use a known conversion factor of signal intensity to electron count, and which can be obtained for the camera. Usually this is done if you have a yield system in your microscope, like with the drift tube. And this sometimes is changing in time and also depends on the voltage of the microscope. The third way is by measuring the current on the phosphorus screen. So the large screen directly reads the current produced by electrons that hit it, while the small focusing screen generates a calibrated output. So as far as I know, most of the new microscopes have the built-in beam current reader, but I would definitely recommend to check the value with a Faraday cup holder. So how do we know what is the best dose for our experiment, and we don't introduce any artifacts in our experiment? The critical exposure is the exposure at which the intensity of the component decreases with about 0.4 below this initial value. So the limiting electron dose for a specific system can be determined from the dose-dependent disappearance of diffraction peaks, which is actually the loss of the structural information. So what is recommended is to record a series of images of which the initial one represents the lowest possible dose in an overview image. So actually, when you sit in front of the microscope and let's say you already have a calibrated value for the current, how do you actually calculate the dose rate? So in TEM, it's estimated by dividing the calibrated beam current in TEM with the size of the illuminated area on the sample and multiplying it by the exposure time. In STEM, things are a bit different. The dose rate is calculated by knowing the beam current, the size of the viewing area, and the frame time. This figure shows the dose required to reach a desired spatial resolution at 200 kilovolts for different materials. For example, the little dose for the E. coli is about 0.01 electron per nanometer square, compared with the reduction of the metals, which is like 100 times bigger. Some typical numbers for doses in cryo-TEM are ranging from 10 to 100 electrons per square angstrom. For example, the pH of the water is expected to change from 7 to 5 as irradiation as small as 20 electrons per square angstrom per second. The dose in water is usually higher than the dose in ice because of the easier diffusion of the reactive species away from the irradiated region in liquid. The resolution in liquid cell microscopy is limited by a few important factors like thickness, sensitivity, and dynamics. In both TEM and STEM, spatial resolution depends on the spherical and chromatic aberration, signal-to-noise ratio, and stability. Resolution in TEM depends on the convergence angle, chromatic aberration, energy beam, and thickness of the liquid and the membrane. The resolution in STEM depends mainly on the thickness of the sample. In both TEM and STEM, resolution is proportional with the dose, which implies that improving the resolution requires a much higher dose, but also shows that there is an advantage to choose slightly lower resolution for beam-sensitive samples. It's also important to know on which side of the window the particles are sitting. So in case of the TEM, the highest resolution for an object in a thick liquid layer is achieved when the object is on the electron beam exit surface. For STEM, this is the opposite. Because of the probe broadening in the high probe broadening, the highest resolution in STEM is achieved when the objects are on the top of the window. So this is one of the bright field STEM images taken with one of our students in a group. It's an image of the Palladium particles, and you can see the resolution is much higher on the particles which are on the top window. This is a table showing different soft materials in the liquid solution and the special resolution achieved in a different cell types. So far, the best resolution was obtained in a graphene cell in water. The worst resolution in this table was found in a fibroblast cell in the silicon nitride window with a flow cell. So in the last few slides, we talked about the thickness and how important is the thickness in the spatial resolution. The thickness of the liquid influences the reaction kinetics or morphology of structure and also affects the beam-induced effect. There are two methods to determine the local thickness. One is by measuring the fraction of the transmitted electrons versus incoming electrons, where we need the thickness, we need the mean free path of the electrons, and we need the electron scattered on the detectors. And the second way is to use the characterization of the energy distribution of transmitted electrons, or it's called the Yield log ratio technique. There are like a few pages of equation, and then we come up with this final equation to measure the thickness of the water. If anyone is interested, they can email me and I can send you all the equations. So in this case, what we need to know is the mean free path, which is easily calculated from if you have a Yield system in your microscope. And we need some values for the silicon nitride windows as well. Now I'm going to talk about some practical aspects related to the thickness. To preserve resolution and maximize signal to noise ratio, microscopists prefer samples and liquid layers that are as thin as possible. Even within thin spacer, due to the enormous pressure differential between the inside of the liquid cell and in the TEM column, the thin silicon nitride windows bow. Bowing leads to thicker liquid layers, which increases multiple scattering and degrades resolution. Depending on the window width, the thickness in the center can be even up to 3 microns. One solution for that is to use chips with long rectangular windows. Orientation of the windows makes a difference too. So parallel orientation gives the larger field of view, but it might not yield to the thinnest liquid layer. The cross configuration, I know that's usually the most used one. In each corner, we have a thin layer, and but we have a smaller field of view. So how do we choose between different techniques? So in TEM, a uniform circular illumination is projected on the sample. The transmitted electrons are collected by the objective lens and detected by the pixelated sensor of the camera. Detection is via phase contrast in the case of thin samples. However, in a thicker samples, phase contrast TEM becomes blurred, and the resolution or limiting factor in TEM is the chromatic aberration of the objective lenses. In STEM, the specimen is scanned by a focused beam, and it does not need a post-specimen objective lenses, which is the main source of the resolution-limiting chromatic aberration. Annular dark field, STEM, is effective for imaging materials for high atomic number in thick liquid layer due to the strong dependence of its contrast on the atomic number. In liquid thicknesses up to 200 nanometers for low atomic numbers materials like the biological samples, TEM imaging is better than STEM. For thicker samples of low atomic number, we have better resolution in STEM or annular dark field STEM. Dose is also important when choosing the mode. In STEM, the total current applied to the sample is actually lower than in a TEM. So if you decide to use the STEM mode in your experiment, there are a few important parameters that are needed to be taken into consideration, like the electron beam current, magnification, and pixel dwell time. The magnification is defined by the area the STEM beam is scanned over. So lower magnification corresponds to large scan areas, while high magnification have smaller scan areas. Adjusting the STEM beam parameters affects the interaction volume and the radicals produced. Increasing the magnification reduces the interaction volume for a fixed fluid path length, while at low magnification, the scan area is large, yielding a large interaction volume. Increasing the electron beam current or slow dwell time increases the amount of radicals produced by radiolysis during the STEM scanning. Limited electron exposure can produce not enough reducing agent for observable nucleation growth. So before we start a STEM experiment, there are some quantification of imaging condition that needs to be done, like the accelerator voltage, electron dose, and liquid thickness. I'm going to talk now about two of the analytical electron microscopy techniques. So I'm assuming that you are a bit familiar with EELS and EDX. I actually had 2 slides about that, then I had to cut. So EELS is the electron energy loss spectroscopy, and EELS in liquid cell microscopy is definitely more challenging than a regular microscopy. This is because of the signal degradation due to the multiple inelastic scattering events. Because we have the window, we have the sample, and also we have the liquid. And that makes it really difficult to interpret the signal. The thickness limitation for valence EELS is nearly twice as large as the limitation for core loss EELS, because there is a little lower energy signal to obscure the valence EELS peak. In these figures, we have the oxygen kh in water as a function of thickness. So the only distinguishing feature of oxygen is observed in less than 300 nanometer thickness. On this inset, we have the same acquisition of the data, but in a low loss region. And we can see that there are good information for thicknesses even up to 650 nanometers. Also, the guys from Mueller's group at Cornell, they did lots of measurements in yields for different liquids, and they found kind of similar results. So when we have thicknesses lower than those values, the core loss and the low loss yields spectra prove meaningful. The arrows here are pointing the optical gap. There were also some STEM studies to study the charge and the discharge of the batteries, especially for lithium iron phosphide, where the electronic structure reveals the material's charge state. So we're going to talk about the EDX now. So EDX, the energy dispersive X-ray spectroscopy. When we do EDX in liquid cell microscopy, we have to do some modification of the holder. So on the left image here, we have the upper and lower pole piece of a TEM objective lens. The EDX detector is situated at angles between 10 and 20 degrees relative to the sample. The yellow area here indicates the path of the X-ray needed to take to be detected. With the initial design, the X-ray could go in the right direction of the holder. So the holder had to be modified to be etched, so which allows the line of sight. So if it's possible, use the modified beryllium plate every time you do EDX in a liquid cell. And also the EDX technique is affected less by the thickness. Some example for EDX in the liquid cell microscopy. On this left side, we have a standard field image and a map, and the spectrum of the same area. So the blue area here, it's actually an area which is covered with water and it's really thick. So by taking two EDX spectra, one from the blue area with the water and one outside, we can see that actually the oxygen dominates the area in the water, and we can actually detect the water with EDX. On the right side, we have some EDX maps of suspension containing gold and palladium nanoparticles. And we also have the silver nanowires, and that reaction has been reduced from solution by the electron beam. So if you need to choose between two of these analytical techniques, this table might help a bit. So before you start, you need to know what elements you have. You also need to know the thickness of your sample. If your thickness of the sample is more than 3 mean free paths, will be impossible to do core loss yields, but it will be okay for the EDX experiments. If you have heavier elements, like with the Z more than 30, you need to focus more on EDX technique. Also, if the dose is an issue in your sample, EDX might not be a suitable technique because it requires long acquisition time. In the next 3 slides, I will present some of the results from our group. Some of them are published, some of them are due to be published. The first example here is from concrete. Concrete is second widely used material in the world after water. So understanding the cement hydration reaction, especially in early ages, which can contribute to early microstructure and strength development, it's critical for both scientific and environmental values. In this study, we monitored hydration reaction of nanoportland cement during the first 24 hours, and we recorded all the phase transformations. These bright field images show the formation of the calcium silicate hydride product and the transformation in time from a small, well-distributed precipitate to a flower-like structure. We also perform ex situ studies, high resolution and diffraction, together with LCEM and EDX to confirm the hydration product. Another example where the liquid cell microscopy is very useful is biomineralization. Calcium phosphate biomineralization is essential to the formation of bones and teeth and other pathological calcifications. Unraveling the mechanism of calcium phosphate nucleation and growth contributes significantly to understand the diseases caused by the pathological mineralization. In this study, we did real-time imaging of calcium phosphate nucleation and growth in the in-situ TEM, which confirms prior results obtained by cryomicroscopy, and TEM indicating that the calcium phosphate mineralization occurs by particles attachment. We also perform yields to confirm the presence of calcium. This is an example where electrochemistry information were acquired during the in-situ experiment. Electrodeposition process is widely used to fabricate tunable nanostructure materials in application ranging from biosensing to energy conversion. In this study, we used liquid cell transmission electron microscopy along with post-situ LCEM to investigate the electrodeposition, focusing on the effect of supporting electrolyte, and we try to shed some light on the nucleation and growth of palladium. We took a series of electron microscopy images, and we recorded current time transients during the electrodeposition to see the nucleation and growth of the palladium. We wanted to check the influence of the HCl on the palladium growth, and we found out the addition of the HCl in the electrodeposition bath transformed the morphology of palladium electrodeposit. These are a few examples which are published in the literature. And I wanted to show that other techniques than analytical techniques can be used in the liquid cells. So one of these techniques is the tomography. And there are some amazing results in tomography obtained by the group of Kim in South Korea. They used graphene liquid cell in a chromatic aberration corrected Titan operated at 300 kilovolts. Using a direct electron detector camera, they analyzed 9 platinum particles and determined where the atoms were located. And also they provided information about the structural heterogeneity of nanoparticles in solution. Structure and strain analysis is enabled by assignment of precise atomic positions, reveals lattice expansions of ligand protected metal nanocrystal in solution, and also the existence of large strain near domain boundaries or dislocation edges and surfaces. High resolution TEM can also be done in really thin liquids using, again, graphene liquid cell. Uke study platinum nanoparticles growth with superior resolution. They found that coalescence is a site selective with a specific facet with the lowest surface energy preferred during nanoparticle attachment. This is a nice case where STEM was used to image gold nanoparticles. The particles were with the average size of 1.4 nanometer in liquid thicknesses actually bigger than 3 microns. So the upper image is from the top layer, the water top layer. So for high magnification, the particles were dissolving in the water. You know, in the image below here, we have the gold particles below the water level of like 1.3 microns. The thickness of the liquid was measured by tilting the specimen and measuring the beam current. So where do we go from here with the liquid cell technique? Nowadays, the spherical aberration correction in TEM and STEM can reduce delocalization, decrease the depth of field, and improve the interoperability of the obtained images. Having a microscope with a chromatic aberration correction improve the balance of elastically scattered electrons focused in an image and inelastically scattered electrons. Also, using a faceplate for TM can increase the contrast by a factor of 5. The camera we get now, the microscopes are much better than before, and they come with an increased detection quantum efficiency. Also, I would say there is a lot of room for improvement in the software required for tracking and acquisition of the data. At the end, I just want to show some of the materials I use for this presentation. So there are 2 amazing books. One of them I call it the Bible for the liquid cell, the book of Francis Ross. And there are so many good reviewed papers actually published not too long time ago, and we have lots of good paper from Ray Egerton, which talks about the radiation damage in the materials. So that's kind of all for today. Thank you for joining. And if you have any questions.
Sorry, I didn't mean to cut you off.
No, it's okay.
Right, so if you have any questions, please put them in the chat and we're going to address them now. So one question that came in is, will 300 kV knock-on damage be a problem for graphene liquid cell?
I would say 300 is a bit too high for the graphene liquid cells. I mean, in our center, we never look at the graphene cell just because it's really hard to make them. But as I said, the best resolution is obtained in the graphene cells. So if you can use lower, that's definitely better.
Okay. Regarding phase contrast imaging techniques, such as faceplate TEM, 4D STEM, example IDPC, and tychography, do you think the thickness of the liquid is something preventing us from using these techniques?
I know in the center, it's only on the Talos 200 we have the faceplate. So it's not the thickness, I would say it's the option we have for the microscope. So I don't know if you are aware that we got the microscope only a few months ago, the Talos 200, so we haven't used too much the faceplate. So that's definitely something we can try in the future. But I mean, in the past we were limited by not having this option at the microscope.